Okay, so let's pull up. Okay, tell me that you guys are good with statistics and, no, not statistics, sorry, calculus. And this is a piece of cake. If you're not great with calculus, you just have to learn a couple of things or remember a couple of things, and you'll be fine as well. I'm having a little trouble with a buffering iPad. No why. Do that again. I probably should reverse the order. I don't know. Okay, so we're going to start with number 3. Look at the story here. So we have to assume M&M model with corporate taxes and financial distress holds. So that's what we just talked about. And that the capital asset pricing model is true. Protect Corporation, Inc. is a corporation financed with debt and equity. $80 million of its assets are financed with debt. Pay an effective annual return of 7% and the remainder with equity. Okay, so this is the market value of the firm. This is the value of the firm. No, sorry, this is financed with debt, okay? And the remainder of its assets, 8 million, okay? An effective annual return of 7% and the remainder with equity. PCI earnings are subject to corporate taxes at a rate of 40%. The financial analyst has estimated that if PCI were all equity, it would have a market value of 500 million. Why am I saying that? Why am I talking about it that way?
Because it's important.
Yeah, but what am I asking? What am I trying to point towards when I say it like that? If it was all equity, so I'm telling you to look at the formula. Which formula? I'm telling you, I'm hinting that the value of the levered firm is equal to the value. So I'm giving you VU plus B TC TCB, right? And then minus
PV.
financial, huh? What happened?
I'm gonna say like FV.
Exactly. Financial distress. So PV, remember this is the present value, right? These were calculated using the approach of valuation, right? So this was all discounted. If you go back to the exercise that we did EBIT after tax discounted. So we're basically getting that amount. Okay, so PV, cost of financial distress. So VU is this. TCB is going to be 0.4 times 80 million. Or B, sorry, the formula. We want the formula. We're not going to put the numbers in, but that's the B for now. And the present value of cost of financial distress, we're going to try this one first and put the formula in there. And that's what's going to cause the curve to go from a line to a concave line. A concave curve, sorry. Got it? So what does that look like? VL is equal to VU, which is 500, plus TC 0.4B, So I'm going to prepare the value of the firm as a function of B and then attempt to maximize it, optimize it. And the first one I'm going to write is EB to the 30. All right, so that's just your function. What is the maximum or optimal level of debt? I have to take the first derivative. Do you guys remember how to do this? What is a derivative? How would you define a derivative? Think about it. It's the slope of a line at a point. It's the slope of a line at a point. It's the rate of change of the line at a point. All right, so maybe I have to do the review. Let's just do it here on the side here. So if you have y, so recall. Let's do it like this so it looks more like what we're doing. Let's call it f of x. If you have f of x equals 500 plus 0.4x minus, oh, let's just leave it like that for now. So if you take the derivative of this is just a line. What is the derivative of this? You guys, no idea? Okay, what did I tell you? The derivative is the slope of a line. What's the slope of this line?
0.4.
Wow. Did anybody else know that? Were you feeling it, thinking it? That's all it is. Let me see if I have a video on this. I must have a video on this stuff. I did some solving there. Okay, well, okay, let's just continue. Okay, so the derivative of the slope of a line. Okay, so what if the function is okay, wait, let me just do an overview thing here, okay? So if you have if fx equals 10, what is the slope of that?
0.
Okay, so y. So what is fx equals 10? What does it look like? Let's see. This is x, this is fx. What does fx equals 10 look like, everybody? I don't know if this is going to help you, but what does fx equals to 10 look like? How would I draw that?
A horizontal line.
A horizontal line where?
At 10 at fx.
All right, so it's just going to be a line like that. And what is the slope of that line, everybody?
0.
No.
Did you see that? So I don't know if it's going to help just for some basic cases, visualize, right? So then we did fx equals, what did I say? 500 plus 0.4x. Okay, so now this is a line. And it's going to pass through 500. And it's going to, so that's that line. So what's the slope of this line? You told me?
0.4.
0.4.
Okay, you guys are getting better. And then what if the function looks like So notice that because 500 is 0, we're going to go step by step. This one's 0 and this one is 0.4. So the slope of this line is 0.4. So what if you have 500? No, let me make something. I'm scared. Don't want to screw you guys up. Okay, so let's do first x squared. What's the slope of that?
1.
Okay, let's look at the picture. What does it look like? What does the drawing of this look like? Some basic stuff, guys. Doesn't it go like this? Right? So now it's not just one slope, right? There's a bunch of slopes. That's why a derivative is the slope at a point. So this one has many derivatives, like depends where, right? If I'm going to put it here, here, here. So basically the derivative itself is a function. There's so many, there's infinitely many, depending where you are. Is that what I wrote here? Derivative is the slope of a line. Okay, so I'm going to say slope of a curve then. I'll change it to curve to make it more general. Are you guys with me? Are you with me so far? You're good? We're getting there?
Yep.
Okay. Okay, so back to this. So it was easy here because this one was just 0. If you take the derivative of a constant, it's just 0. Take the derivative of a line, it's just one slope. But this has infinitely many slopes. So the derivative is another function. And what is the functional form of the derivative of x squared? Do you remember? What does it look like? It looks like a line. I mean, it's going to go, if I did this infinitely, these things along here, these slopes along here make a line, and the function of the line is 2x. So there are different derivative forms that you have to learn, and that's what's on the sheet that I give called calculus handout there online. So the square one is just 2x. In general, any power function fx, oops, if I have a power, the derivative is always to bring the constant, well, the multiple here, or the exponent, down, and then multiply by 1 less, x to the power of 1 less. That's what that is. That brought the 2 down, and then I reduced the power 1. So it's going down in power each time you take a derivative. So again, another example. Let's do another example. Fx equals 3x4. What would that be? What would the derivative of that be? Come on, guys. I have more to do. 3 minutes left.
Is it 2x to the power of 3?
It's 12x to the power of 3, because that's going to come down and then you multiply. All right, so let's do, what's the question that you have? E, what's the derivative of e to the x? Do you know? This is a very neat one because the derivative of e to the x actually turns out to be the exponential function itself. So that's why it's used a lot. It's very interesting. Okay, the rate of change at any point is itself If I change that a bit, let's put a constant in front. So what is the problem that we have? Sorry, let's go back for a second. Ours is EB30. Okay, let's do that. So well, let's put something in front. So let's say 2EX. What's the derivative of that?
The same.
The same, okay. And what is the derivative of 2E 2x? Well, let's make this another number so it's not too many twos. What's the derivative of that? And then I'll do the last one and then we'll go. And you guys are going to work
10,
on this. Mm-hmm.
10E2x.
Okay, so what she did there, let me do it step by step. So it's itself, but then using what's called the chain rule, you have to multiply by the derivative of this because it wasn't just an easy x. It wasn't just x, it has to have a derivative too, which is 2. So that's why you got 10e2x. Good. All right, so now the one in our problem is fx equals, go back, b30. Okay, let's do that, x over 30. What's the derivative?
EX over 30.
So it's itself, like that,
Mhm.
times the derivative of this. So what's the derivative of that? In other words, what is the derivative of x over 30? It's just the constant in front. Like x over 30 is the same as 1 over 30x. It's like back to this one here, right? Because this is a line with a slope. 1 over 30 is the slope. That's what the 1 over 30 is. Just see that as this. So it's just like this one over here. So then this is 1 over 30. So I can just put it in the front. All right, I'm going to do that. And then before you go, I know it's time is up, but what about the other one on the page there? We have this function here. What is the derivative of logarithm? Do you know? I need to make this smaller. It's bothering me. I'm going to make that smaller and erase this one. So what's the derivative of
It's
logarithm?
1 over x.
Isabella
So
knows
that one would be
derivatives. Good for you.
2 over x, I think.
Yes. So fx, so all these derivatives, and I said like these basic ones are the important ones. The derivative of log x is 1 over x. So the one that I gave you on the assignment was log b, but anyway, it's just the last one here. I'm getting bigger and bigger. Is fx equals 2 log x. The derivative is equal to 2 over x. All right, a log function Okay, the exponential function goes like this. No, I'm doing this. Am I doing this right? E to the 0 is 1. Yeah. So this is 1 here. So this is e to the x, and then through this diagonal is the log function, like this. This is y equals e to the x, and this is y equals ln x. And it turns out that the first one of those exercise problems in the exercise, that you're going to be taking away positive numbers. So your value of the firm will be going like downsloping, but in this one, the value of the firm will be up. So anyway, because this one is going the other way, it's going to have the opposite effect. So you guys work this weekend on that stuff. Let me know if you have any questions. I believe, let me check here before you go, or if you've already gone. I'm just going to check those videos and see if I do this problem, which I probably do. Let me see. I don't think I taught it without doing the problems. Oh yeah, I do it. So on that video, I solve this. Okay, so you're not left hanging. Like, what do I do? Understanding it is another thing, but you guys can let me know if you don't get it. Okay, so on this video here, I actually solve those problems at the end. You see? It's all here. And like you have to take the first derivative, then you have to solve. Oh, this is messy. So you take the first derivative, and then what you're supposed to do is set the derivative to 0 because you're trying to find where it hits the optimal point. So then you set that derivative to 0, so you're going to get this line, not, of all the infinite lines, you want this one and this point. So you set it to 0, you solve for it, and you find where B, or the debt, is optimal. And then you verify that that's maximum. And that's it. It's not that hard. This is just forcing you to remember calculus. But for a practical purpose, what's the optimal level of debt? Come on. All right. Any questions? So you also have the calculus handout for weird looking derivatives, but I think I really work on those two exercises. If you don't have any questions, I'm going to say bye because it's 3 o'clock or 3 o'clock here, 4 o'clock there.
Thank you, Professor. Have a nice day.
Thank you,
Thank you,
Professor.
Professor.
Thank you, Professor.